Switch it. Now you can hear me. All right. We're going to start in just a minute, guys, so come on in, find a seat, and we will get meta. All right, I'm going to kick it off. This is Android Metaprogramming. I am Audrey Troutt. I put my Twitter handle down here on the bottom, Oddity. If you want to send me questions, we got kind of a big group here. If I'm able to answer them at the end, I will. If not, I can follow up with you afterward. I love talking about metaprogramming. So what is metaprogramming? What do I mean when I say metaprogramming? Metaprogramming is writing code that reads, generates, analyzes, transforms other code, or even itself. This can take a lot of different forms. It can be done at runtime, or compile time, or even with source files. You're probably benefiting from metaprogramming techniques today, even if you don't realize it. Libraries like RoboJuice and Android Annotations and Dagger, these are all using annotations, which are metadata, to inject new behavior into your app, which is metaprogramming. So why would you use metaprogramming as a developer? There are a lot of reasons. Sometimes you want to eliminate boilerplate code or generate some code that is complex and easy to get wrong. Maybe you want to inject some extra functionality into an app so that the developer doesn't have to do it. Or maybe you want to analyze some code to check for bugs or best practices. There are about as many reasons to use metaprogramming as there are for programming in general. But let's take the reason of eliminating boilerplate code. A lot of the popular libraries today do that. What does that look like? You guys have probably seen this, but I'm going to show you an example anyway. This is from RoboJuice. On the left, we have a sample activity, and it's implemented the typical way, all the boilerplate code. And the code on the right, using the RoboJuice library, is cleaner, easier to read. It's easier to read, it's easier to refactor, it's more flexible. The boilerplate code for find view by ID, or setting the content view, or getting a reference to that location manager, it's gone. And you can see what the meat of this activity is made of. Everybody wants to reduce duplication in their code and eliminate boilerplate. Metaprogramming is what makes that possible. Obviously, people have already done the hard work building RoboJuice and many other libraries. But if your needs don't line up with what existing libraries provide, you might find yourself exercising metaprogramming techniques to create a tool. And that's the most common reason why you might use metaprogramming techniques on Android, because you're a library developer. Library developers have to develop generic solutions to problems. Sometimes a static library, which is just providing an API call or a wrapper around HTTP calls, isn't enough. That's not always the kind of problem that you're trying to solve. Removing boilerplate code or adding a layer of new functionality on top of existing app logic can't be done without metaprogramming. As an SDK developer at Artisan Mobile, I had an opportunity to invent solutions for working with other people's app code on both iOS and Android. When I was building the Android SDK for Artisan, I was challenged with automatically collecting analytics events for user interactions. So I had to do this without any pre-knowledge of what the screens would look like or what kind of views would be available to tap on the screen. And I had to implement this with minimal help from the app developer. That was our mission. So I drew inspiration from the work that I had done on the iOS platform. And bear with me, I'm going to show some Objective-C at an Android developer conference. But that's because metaprogramming is easy on iOS. It's baked into the language. There are three different things I want to show you from my work in iOS development. Categories, swizzling, and perform selector, which is a handy little method. Up here on the screen, this is an example of an Objective-C category. Categories allow you to extend existing classes loaded into your app's runtime, even classes that are part of the base iOS package. So UI view or UI view controller, this is like view or activity. This here is an extension of UI label, which is like a text view on iOS. You can actually add new methods and new fields onto those iOS classes, and as long as this class is included with your app, you can use those methods just like they were baked into iOS from the beginning. It's an incredibly powerful tool. In addition to that, in the Objective-C runtime, there's a tool called swizzling. Swizzling gives you the ability to wrap or even completely replace method implementations on any classes loaded with your app. And that includes those base classes that are provided to you as part of the iOS runtime. So UI view controller. This example here, I have a method which takes in an object and a selector. And a selector is kind of how you can think of like a method, or a method name with the parameters that defines some sort of function on that object. It takes a replacement object and another method, and this actually completely switches the two, right? So the original class, like maybe it was your view controller, has a view will appear method. You can actually entirely redefine what that method does. You can do this at runtime, and as all of the view controllers that are loaded into that app are executed, they won't execute the original code, they'll execute your new injected code. I put a comment in there because this is very, very naughty behavior. You never, ever, ever completely replace the code. It's polite to call through to the original implementation as a library developer. This is a powerful and dangerous tool. You can break an app beyond recovery by screwing around with swizzling. You can also accomplish amazing feats of metaprogramming. For example, if I were building an analytics library, you could swizzle UI view controller to insert your own call every time a screen appears, maybe log an analytics event. So there you have a method called view will appear. I could inject my analytics tracking call right at the beginning of that. Another feature on iOS is a little method called perform selector. Perform selector is available on all NS objects, basically all objects, at runtime. You can try to invoke any method on any object. Public methods, hidden methods, even undefined methods, good luck with that. This isn't by itself metaprogramming, but it was definitely a handy tool in my metaprogramming toolbox on iOS. Combined with categories, which are extending these classes, and swizzling, which allows you to replace existing implementations, you can now read, add, redefine, and invoke any behavior on any object in your entire app. These metaprogramming tools are all baked into the language. And these features of the Objective-C runtime inspired me to start looking in the Android runtime, the Android libraries, for similar opportunities to inject my code into yours. And that's basically where this talk came from. The first place that I looked for metaprogramming possibilities on Android is to Reflection. The Java Reflection API is provided as part of the Java Lang Reflect package, and it's very meta. With Reflection, you can inspect your classes, their annotations, their fields, their methods. You can invoke methods, and because you can invoke methods, you can change the values of fields. What does that look like? Here's an example of reflection being done at runtime. I created a log property value for object method. I love that name. So here, in the first step, can you see that highlighted at all? No, barely? Okay, number one. All right, so here at number one, you see I am getting a reference to a method on my class. So this private method takes in an object and a string, which represents a method name. So I look on that object for a method, an implementation that matches that string name, and I hold on to that reference to it in a method object. Second, I set that method to accessible. That's because from the scope where I'm actually executing my private method here, it may be a private method that's not accessible to me. And just setting that to accessible tells the reflected object to suppress warnings about that. And once I've done that, I can invoke that method on the object that was passed in and capture the return result. In this case, I'm just logging that out to the console. So here's what it might look like to use this private method that I wrote that uses reflection. It's dead simple. It's just a method call. I pass in the object. In this case, I have an activity, and this is my onStop method. And so I'm going to pass self in, which is my activity, and I'm going to pass in a string which says time on screen. So what the effect of that will be is that I will get a reference to the method time on screen, which you can see defined at the bottom. I will set that method to accessible, invoke it, capture the return value, and log it to the console. Reflection is a handy runtime tool, but it has some limitations. For one, if you don't already know, a reflection on Android is so very slow. So make sure this is not code that you're running, certainly on the main thread or in anything that a user is staring there waiting to complete. As an SDK developer, we built out a feature that does A/B testing. It enabled brands to modify arbitrary properties on arbitrary views in their application. And this was something we wanted to be able to do just before a screen appears. And we found that brute force coding, to just invoke the right setter for the right property on the right object, ended up being faster than reflection. And the code complexity was really the same. At the Reflection, No Reflection talk yesterday, Stefan Nicola from Groupon, he had some hard numbers from research that they had done with RoboJuice on exactly how slow reflection was compared to calling the methods directly. It was on the order of 3 times slower for accessing fields and 10 times slower for calling constructors. This is a serious difference in performance. Another limitation of reflection is that reflection by itself does not allow you to modify the behavior of the code. You can change values, invoke methods, but the execution path itself is the same. This is kind of similar to me to Perform Selector in Objective-C. It's a handy tool in your meta toolbox. So when would I ever use reflection? I mean, like most metaprogramming, reflection is good when you don't have access to the code that you're modifying. Maybe this is somebody else's code. Maybe this is code you haven't written yet. It's a generic tool. It's useful in those situations. There's really not much else you can do. Yeah, so this example I gave above, the reflective method that I wrote could actually be an implementation that's injected into the app. It could pull those parameters from an annotation, for example. Speaking of annotations, that's the next place I wanted to look when I wanted to do metaprogramming on Android. Annotations are so meta. We use them all the time. Just baked into Java, methods are marked as @override or deprecated. The annotation itself is metadata about a piece of code. And like reflection, annotations are an important tool for metaprogramming. As you may already know, all of the popular dependency injection libraries, RoboJuice, Dagger, Android Annotations, they are using annotations. Here's an example of one in the wild. This is from Android Annotations that has the background annotation. The effect of adding that annotation onto your method, assuming that you're using the Android Annotation library, is that this method execution will be wrapped in the appropriate boilerplate code for backgrounding. They have a counterpart for the UI threading as well. What does it look like to define an annotation? It's really quite simple. I made one here, which is called watched method. I used to build an analytics SDK, so a lot of my examples come from that. So a watched method is targeted at elements of type method. So this is an annotation that is going to go onto methods. I've indicated that it should be retained even at runtime, because maybe I want to use some reflection to identify those classes that are annotated with watched method, and they can take parameters. In this case, I've defined 2 parameters for my annotation, event name and log property. For log property, I've given it a default value of an empty string, no property. And here's an example of what it might look like. Again, in my activity, my onStop method, maybe I wanted to annotate my onStop method as a watched method. And the event name that I want to log is disappear, it's just a string. And the property that I want to log is time on screen. That may look familiar. So those parameters would get parsed by an Annotation Processors. There was a really fantastic talk earlier today by Michael Evans, and talked in detail about Android Annotation Processors and gave a concrete example of how they work. So if you missed that, you should definitely check out the video later. But basically, the idea is that since annotations themselves are just information, they don't themselves add that new behavior into your code. They come alive with annotation processing. When you add an annotation processor to your project, it gets a chance during the build process, before compilation, so after you're done writing your sources, before compilation happens, it can generate additional source code. It can even trigger a compile, and that gets combined with the rest of your application code that goes on to be dexed and added to the device. Annotations and annotation processors work particularly well for generating code and eliminating boilerplate. These are very useful for reading, analyzing code, and they are a standard, widely used Java tool, but there are some limitations to Android annotation processors as well. And one limitation is that you can't modify existing implementations. You can only extend or add new classes and methods. Another potential limitation is that you need some help from the app developer to bind your generated code into their app code. This is something that app developers are pretty comfortable doing. We're all familiar with annotating our methods, but depending on what you're trying to do, this may be a drawback. And finally, anytime you're generating code on Android, you have to be mindful of the impact on method counts. You have to be sensitive to the dex limit and other considerations. No one's going to thank you for making their life more difficult by putting your library into their app. So annotations and annotation processors aren't the only way to get meta on Android. This is the really serious stuff, I think. Neither reflection nor annotation processors have the ability to modify those existing implementations. I mentioned that twice as a limitation of both of those tools. But bytecode manipulation can. With bytecode manipulation, you can analyze, you can generate, you can transform. You can do this without any annotations, or really without any input from the developer at all, as long as your library is included in their project. In the Android build process, as I mentioned before, annotation processors they do their work before compilation, before the green circle that says .class, I think. This is Java compiler, before the .class files are generated. So they're working directly with the source code, generating new source files. Bytecode manipulation is working with bytecode. Bytecode is those .class files. And even some tools for bytecode manipulation work with the dex files as well, which is the second form that your code gets converted into before the final app package is built. There are a couple different tools to choose from for working with bytecode. If you've looked into annotation processing and it isn't the right fit for a use case, you're probably going to want to check out one of these libraries. I've ordered them here from lowest level at the top, weirdly, to highest level at the bottom. So with ASM is an extremely low-level tool where you're working directly with bytecode. The code that you're writing, you'll have to know the Java bytecodes in order to be able to match up to the right methods. DexMaker is around the same level, and I honestly haven't used it, but DexMaker claims to make it possible to even work in runtime, to modify Dex code at runtime. Java Assist is a little bit higher level. The code that you're writing looks a lot more familiar. It looks like Java code. And yesterday, I learned that Realm is using Java Assist and Morpheus, which is a Gradle plugin that makes that possible to do some of the cool work that they're doing. And finally, at the highest level, the most familiar looking code probably to Android developers is Aspectj. This is arguably the easiest to work with. I'm going to show you an example a little bit later, but first, what might it look like to do bytecode manipulation in Java? And so this is an example using the Java Assist library. This is one of the higher level tools. So imagine this is code that's being executed after your class files have been generated before dexing, right? So this is a process, this is running as part of your Android build process. At step one here, I am getting a reference to the class. In this case, my class is child, and it's the test package. And I'm going to set a superclass. I am modifying the inheritance of this child class and setting parent as the new superclass. On the same class, I'm getting a reference to an existing method. The method is called say, and I'm going to insert my own logging code before the existing implementation of the method say. At number 3 down here, I can take that same class, that same method, say, and I'm going to wrap the entire thing in a try-catch. In this case, I'm just going to log the error out to the console to make sure it doesn't get thrown and crash the application. And finally, you can write all of that back out to the file system. So you can see the power of this could be. So maybe I just took one of the activities in your app, And I redefined inheritance. I made that extend Audrey's activity instead of activity. I redefined the implementation of one of your methods. I injected my own logging into it. And I wrapped the whole thing in a try-catch to make sure that I didn't crash your app in the meantime. Since most of the work with bytecode manipulation is done at build time, there isn't a performance impact of using these tools, like there is with reflection, for example. But just like with swizzling on iOS, it's very easy to break an app by messing with its bytecode. When things do go sideways, it can be hard to figure out what went wrong. There's not a whole lot of tooling support here. And speaking of tooling, Stephanie Nicholas yesterday made a great point that we really don't know what the impact is going to be of the upcoming changes with Jack and Jill. Are a lot of the tools that we're using for bytecode manipulation still going to work when we're doing more incremental compilation? We don't know. Another limitation of using bytecode manipulation that you should be aware of, it's not something that we tend to do as Android developers or even as a Java developer, any sort of developer. Working with the Android builds process, understanding bytecode and the implementation of those methods on that level is very unfamiliar. So this can make for a much longer ramp-up time for a project like this than you would have the typical application or a static library project. Aspectj, as I mentioned before, is another tool for bytecode manipulation. It was designed to support aspect-oriented programming in Java, aspect-oriented programming, also known as AOP. AOP is a programming practice which is about looking at aspects of your app's behavior. An aspect could be logging or security or analytics. And the code responsible for handling that aspect is then pulled outside of your typical object-oriented hierarchy of your existing application code and all of your business logic into separate aspect code and then injected back in at build time or even at runtime. As a tool for bytecode manipulation, Aspectj can inspect code, can modify existing classes and methods, and it can also add new methods and classes, just like all these bytecode manipulation tools can do. And it's pretty easy to use if you get used to the vocabulary and a little bit of new syntax. Speaking of vocabulary, Aspectj itself is an extension of the Java language. It's a library, there's a jar that you use, it has its own compiler. I already mentioned the word aspect. Those are those cross-cutting concerns like logging. And when you're working with Aspectj, you define point cuts. This is a word you'll see with other bytecode manipulation libraries. But point cuts cut your application's execution flow at particular join points. Point cut, join point. Join point is like a method call, right? So I'll show you an example of what these look like in just a minute. I actually have some aspect code for you. You then apply advice at those point cuts. So I cut into your application, maybe when your activity on start, your screen's about to appear. Cut in there, I apply my advice. That's aspect-oriented programming. So here's an example. At point number 1, I have defined a point cut called onViewClicked. This matches any execution of any method with any name that returns any value that takes a view as a parameter. Also, if it is inside an activity or a subclass of activity, or inside a view onClick listener or a subclass. This would work for anonymous interclasses as well. So I've defined this point cut, which cuts the execution of your app for any activity, any method inside an activity or a view onClick listener that takes a view as a parameter, basically, regardless of its return type or name. I then define this advice, this before advice, which I match onto that point cut. So before, and it could have before, after, or around. Before any of those point cuts happen, I want to inject this method implementation here on ViewClicked. And it just simply calls out to a static method to log an analytics event, surprise, surprise. So this file, my Aspectj file here, if that's included with your project, during the build process, right, so after the code has been compiled before it is indexed, the Aspectj compiler would take this aspect code here, and take your existing application code and weave those together, inject that advice in, which is really, it's doing the bytecode manipulation for you, and this is the language that you use to control that. With Aspectj, you can not only wrap existing methods, inject new code, but you can also inject new classes and new methods using something called inner type declarations. So here I have an example, just like with the Java assist code I showed you before. I'm actually going to change the inheritance of your activity. So I've taken my main activity and I've made it extend Audrey injected activity. Similarly, I take that same main activity and I've now injected a new method implementation. This is a method that didn't exist before. I call it injected method activity. Wow, that's a terrible method name. Anyway, it has an implementation for just logging something to the console. But once this is woven in with your existing app code, this activity now extends my activity, and it now has this method available on it. So I can get a reference to your activity and call that method, and it will have the implementation that I've designed for it here. With Aspectj, just like with other bytecode manipulation tools, performance is fine. All this work is done at build time. There isn't an impact on the runtime performance. But Aspectj had a huge limitation for what I wanted to do when I was a library developer at Artisan, was that Aspectj can't modify classes that you don't have the source for, that aren't, what they say, part of the compilation. So that means classes that are part of the Android operating system, classes like activity or view or text view, you can't actually modify the bytecode for those classes, only those that are part of your app. This meant we had to lean on a lot of inner type declarations to get around that. Our first approach to auto-instrumentation for analytics was to use Aspectj when I was at Artisan, and developers hated that. AOP was as close as we could get to iOS's categories and swizzling and the Java runtime, this kind of drop-in solution to metaprogramming, but the tooling was very awkward. It was also fragile because the inner type declarations had to be generated with every build to be kept up to date. There wasn't a lot of plugins existing for, at that time it was Eclipse and Ant builds. But even with Gradle, the Android build tools and the Aspectj Java build tools hadn't been married together yet. And they still haven't as far as I know. Because of this, I still don't recommend Aspectj for other libraries on Android unless you're willing to do a lot of work on build tool and IDE integration. And that's basically it. I've given you an introduction to metaprogramming on Android. So what steps can you take if you want to get started? First and foremost, I always recommend leverage the existing libraries that are out there. Odds are, the most common problems that you're going to solve on Android can be solved with existing libraries, with an everyday sort of app kind of injection stuff. But take it a step further and dig into their source. They're all open source. These are well-written libraries. I've taken a look at several of them recently. Go look at their annotation processors and see how they work. Go look at that talk from earlier today, the video of that from Michael Evans. He had a sample project called Aftermath, which is up on his GitHub that you can check out. When you're ready to get started with your own metaprogramming project, those open source libraries can be useful models. For public general use libraries where you're primarily generating code, it does seem like annotation processors are the way to go. If, like me, you have a unique use case where annotations are off the table, give yourself a generous runway for this project and get to work. It will not be easy, but I've shown you a few options for tools. One word of advice I have if you go this route, build tests around manipulated code so that you can hook that up with continuous integration. You will thank me later. And finally, speaking of thanking, thank a library developer. As I've shown you in this talk, there's a lot of complexity in providing the metaprogramming benefits of your favorite libraries. Metaprogramming can make for a cleaner, more flexible, and it can make you a more productive and efficient developer. But building these metaprogramming libraries requires careful attention to make things work consistently and correctly, most importantly. So I'm grateful for so many open source tools that make my job easier. So I think we have 10 minutes left, but I'm going to go ahead and check if we have any questions, and if not, thank you so much, and I'll see you guys around.